It's a pleasure to follow Paul. I'm an admirer of his writings and his push to make a return to the moon something that we go back to. It's something that I've been pushing for a long time, probably half my career, or half my life, I should say. And unfortunately, it doesn't last long as far as policy goes. So what I want to talk about is really the structural engineer's perspective. To go to the moon, to create a habitat where humans can live and survive as a basis for future exploration, not as a one-shot. So just a few interesting slides. This is a picture from a Russian newspaper called Evening Moscow, where they celebrate Yuri Gagarin's trip into space. Here's from Florida Today. On top, the first Apollo astronauts on the moon, and at the bottom, President Nixon at the time speaking to them, congratulating them, and some early concepts. So one of the things that may not be as well known as it should be is that while Apollo was going on, people were actually designing and thinking what the next steps would be. So Apollo, for a large portion of the community, was not seen as going there and stopping and that was it. It was really as a first step, and part of that first step would be to design structures, and the Army Corps of Engineers had a 1963 manual this thick on a research center for the lunar surface. So a lot of stuff was going on, and basically was cut short when we stopped doing that. Here's some early Boeing concepts. This is basically, you'll see a lot of these concepts are soup can kind of structures, because they're the strongest structures for being internally pressurized, which they would have to be for human habitation. This is showing you a concept for 6 people for a 6-month stay on the lunar surface. You can see the people on the bottom right for size. The other thing you can see is the shielding, which is required for any surface structure. You can see on the top, and also at the insert perhaps, how regolith would be vacuumed from the lunar surface on top of the structure. And even though this concept doesn't show it, you really would have to shield from all sides to shield against the radiation and micrometeorite impacts. So here's a whole list of things that one would have to really deal with as far as designing a structure on the moon. So as a structural engineer, structures are important, but human survivability is more important. And certainly a lot of the issues that are unresolved as far as humans living on the moon is how will they survive. So Paul mentioned about the fact is, can humans survive in a 1.6G environment? And that's an open question. Some medical doctors who are much more knowledgeable than I am on this issue say that anything off of 1G is not survivable without intervention, gene therapy, other kinds of things. So human psychology, physiology, plant physiology, all these things are really issues that are as yet unresolvable and not really resolvable very easily unless we actually go there and start doing testing. So then there's all kinds of thermal issues, structural issues, power systems, which I'll talk about a little bit in more detail. And at the bottom, and again, this is not meant to diminish the importance, is just the economics of it. Clearly, the economics is critical. It's the thing that's stopping us from doing it as much as medical science is stopping us from doing it. So it all is part of the larger picture. So the lunar environment, from an engineering point of view, 1.6G, we have to internally pressurize the structures so that humans can live in there. Anywhere from 10 to 15 psi would be acceptable. Protect against radiation and micrometeorites from the environment. Insulate against temperature differentials on the order of 250 degrees Celsius. And many of the surface structure concepts use regolith as the shielding agent, somewhere around 10 feet of regolith. Other environmental factors, the regolith dust we found from the Apollo era is extremely carcinogenic, and also it's microscopic with very sharp edges, like a micro razor blade. It worked its way into the astronaut suits, it worked its way into machinery. It was not predicted before the Apollo astronauts first walked on the moon, and it had to be dealt with in maintaining machinery. I put here moonquakes. We did a recent study on it. It's not a critical issue as far as structural dynamics, but it's there. We observed magnitudes on the order of 5 Richter And the difference between moonquakes and earthquakes is that the moonquakes last a lot longer and may have certain kinds of effects, maybe not on a structure, but maybe on some more fragile kinds of electronics or components. And then again, the human physiology. So energy production is one reason that people have put forward to go to the moon. There have been a lot of interesting ideas. I think one of the most interesting was put forward by Shimizu, where they would wrap a belt around the moon of a sizable width of solar panels, and those solar panels would then gather energy, project it back to Earth. It's a very nice image. Mining for all kinds of materials is another example. I would say that probably the resources that are on the moon are most valuable for use on the moon, for first settlements. Tourism. Tourism has been put forward for many years as a driving economic force for going back to the moon and various orbits. This is a nice image drawn by Peter Inston, a London-based architect under commission from Hilton, I think around 1990, for a lunar surface Hilton. So Hilton actually wrote a paper, I think it was in '67, talking about hotels on the moon. So Hilton has thought about this for a long time, and you can see how this looks. I might not have put that huge meteorite heading toward New York, but that's just me, you know. It's exciting enough to be on the moon without being under a meteorite attacking you, so that's fine. This concept for a hotel did not work, so Marriott went to version 2. Hopefully nobody's here from Marriott. So this is a more lunar surface Marriott. Basically, again, shell types of structures can resist the internal pressurization. You can see some people floating around there and enjoying themselves. This is a microgravity swimming pool. So if you put a fluid in lower or very low gravity, it basically wants to become a sphere due to surface tension. So this is a swimming pool where there's no buoyancy. So if you swim down it, if you jump into it, buoyancy is not going to push you out. So you got to swim out of that. So you can see this is just a nice illustration of some different things that will happen if you try to go to some of these bodies. Here's a lunar surface, a stadium, very, very high. You see people jumping 30, 40 feet without a problem. I read a paper where there was an NFL football player who went and briefed NASA on sports on the moon. And one of the things he suggested was, obviously, at 1/6 gravity, a lot of things become a lot different, and the scale changes quite a bit. So he said, not only will you be able to throw the football much easier, but you can also pick up your mate, your teammate, and throw him through the goal as well, because of the low gravity. So a lot of different things that can be done. So these are some images by Carter Emmett, who's at the Museum of Natural History in New York, and a space artist as well. And I believe these are Mars, although you can't really tell, but he had some concepts for what surface structures might look like on the moon. This is a fairly well-developed facility with solar panels and all kinds of structures. Here's another one where solar panels are used to line a crater to create a energy receptacle. Again, so I think this is Mars, but similar ideas could be used on the moon. Here's another one showing pressurized habitats. In the back there are greenhouses, which you can see a little bit better in the next drawing. So this is from inside the greenhouse. So you can see there's an envelope which is basically clear, or more or less clear, for light to come in. The person working inside is without a spacesuit. There's a person outside with a spacesuit, and they're growing plants, which will be part of any facility. Here's a very nice illustration by Gary Kittmacher from NASA. It's a very large inflatable kind of structure that's rigidized. So one of the concepts for a surface structure is to have it folded, so you can actually just bring it there and then inflate it, then make it rigid for a permanent habitat. So this is an advanced concept like that. Look, if you can see it closer, I'm not sure how well you can see it. It's basically, I think, 5 or 6 stories, and the people sleep at the bottom because that's the most shielded area. Then further above them is plant areas where plants are grown, and further up are electronics and other facilities. So this is also an inflatable concept. It's like a toroidal structure. The concept was by some people from T.D. Lin engineers. This is from the mid-'80s. Basically, you unfold it, and then the toroidal structure inflates, and then the larger dome inflates. And they actually filed a patent for it. And hopefully, I guess they're still waiting to be called. Here's a nice concept, basically where a crater is cleared out and cables are suspended around it, and then it would be covered and pressurized. The whole volume of this crater could be someplace where you can, if not put people, at least put facilities that require a large volume. Some of these coming slides talk about Russian concepts. Actually, I think some of these are maybe Soviet concepts. For very large facilities on the moon, they call it 2050, but probably this is 2150 really is more accurate. But basically very large structures, you can see a little bit here. A top view where we've translated some of the Russian. You can see basically a whole city on the lunar surface for hundreds of people. Also, many people think that the surface structures really will not be the final form of habitation on the moon or even on Mars, that subterranean structures will most likely be the dominant mode because of the issues of radiation in particular. And so you can see here where in this Russian concept, a large area has been excavated, that's in the light gray, and then the whole city has been built, and then it's all covered up except for very small amounts of structure. Here's one in a lava tube. So lava tubes have been found on the moon, perhaps not as large as this one, I'm not sure, but the idea is that lava tubes exist from earlier activity, seismic, not volcanic activity. You can correct me if I'm wrong on that, but and so the idea is to build in those and basically have a place where you rigidize the lava tube and you have structures down there that are shielded against all the bad stuff that's on the surface. So one of the problems, obviously, and we learned a lot of this especially regarding the space station, but even from Apollo era, is it's very difficult to construct in space. The astronauts get overheated, they get exhausted. The astronauts cannot be our construction crew. So unless we can do it robotically in some way, it's hard to conceive of how we can build large cities on the moon or Mars. Or the space station took a very long time because it's just extremely complicated to do that. And so there are issues of radiation. Here is an image, a pie chart showing the various elements on the moon. And you can see that, as was said earlier, oxygen is a very important part of that, but there's a lot of other elements that we need for an industrial society existing on the moon. And so one of the ideas is to use in situ resource utilization, ISRU, which has been a major thrust of many people, in particular NASA, to try to see whether the resources are already there or almost all already there, that we can then send automated systems to begin construction on the lunar surface so that the structures or most of the structures are already there before astronauts even get there. So this is an example from NASA where you can see it's an automated system that is building an igloo kind of structure on the lunar surface, primarily from local regolith resources that have been processed. So we did some research over the past, I guess, 20 years, just looking at structural analysis. We picked a prototypical structure like this igloo. It's basically two tied metal arches with a base. And so this half circle, this semicircle is the cross section, and it should be internally pressurized. And what we did is we basically designed it using standard Earth-based design techniques to see whether we could get something that would work. So here's a cross section. It's 5 meters high. Has internal pressurization. You can see the arrows pointing out. It has the regolith shielding on top, so that's the dead load on the structure. It turns out that the design load, the design that we have to worry, the load we have to worry about is the internal pressurization. So even though we have a lot of regolith on top that sort of counters that pressurization, the internal pressure is really the consideration for the design. And then we have the foundation in blue at the bottom. And so these are some computational models showing deformations and stresses, thermal analysis. So I know it's hard to see, but I believe these will be put on the Marshall website. So you can see that obviously the red is hotter, the blue is colder, and so we can see, depending on where the sun is located, just the flow of thermal energy through the structure. So all these things are designable. There's nothing that's there from the engineering point of view that we say, well, we just can't design a structure for this environment. So we did that. So here's a vibration analysis, just showing how the structure will vibrate due to a particular kind of loading, and some seismic analysis. So seismic, we were curious about. There's been a lot written on seismic, and quite frankly, a lot of it is very difficult to follow and very cryptic, and the data just isn't there to fully characterize the lunar surface. But from what we know, it can have an impact on certain kinds of structures, but not this one. So this is just a vibration analysis again. And whenever you internally pressurize a structure, the biggest concern is the air is going to leak, right? You always think air is always going to leak. So how do you join something on the lunar surface and make sure that it doesn't do that? So this is a concept that we conceived of a number of years ago as part of our igloo kind of structure. And just an end plate analysis, just showing that all the tools that we have on Earth really can handle the structural problems. And when you design something, you have to also design for construction. So that igloo then would have to be designed and built in stages. So one of the things that perhaps is not really thought about much, unless you're a structural engineer, is that you have to design something that will stand and support its own weight as it's being constructed. Right? It can't work only at the end. It has to work at every stage of the construction. So here we have the base of the structure. We have temporary scaffolding. We put the first arch in, and the second arch will go in. It will all be coupled. So you have the structural framework, which then would be capped and then internally pressurized and sealed. So this is we had a symposium at Rutgers a number of years ago, and we had an artist from the Star Ledger who came down. And so he put some meat on the bones of our structure. So he shows the shielding on top. The nice thing about the igloo kind of structure is it's modular. So you can make almost any configuration you want. You can connect them to what your needs are. So this is a nice, just to conclude, this is a nice ad from Century 21, the realtors. I think this was 2002, I don't remember exactly. So they were obviously promoting Century 21, and I can't read it on this picture here, so I'll have to go here and read it. So, brand new residential subdivision, just 238,000 miles from Earth, features Big Bang design by a world-renowned architect. Could commute on the shuttle, no longer. Full and half-trader lots available. Inquire at the Benaroya sales office. So obviously, very futuristic thinking. It's really great, and maybe that will happen one day. But it's just a nice thought. Thank you very much.